Jai Hind everyone. So in this series of lecture, computer network, we will discuss about error correction and detection. So this is Dr. Avdesh Gupta from CSE department. We will discuss the layer 2 error correction and detection. So what we'll discuss in this presentation, there are different types of error, the redundancy, detection versus correction, and forward error correction versus retransmission, the coding and modular arithmetic. So basically, what is error? First, we have to understand the error. Error is the difference between the observed value and the actual value. What are the actual value and what we have observed? If these are difference, how much difference? So this is the error. If both are same, then there is no error. So in computer arithmetic or in computer networks, or we can say in computer, if everything is transmitted in the form of bits or bytes. So like for example, there is a data like this is a data. This is a data. We have to transmit through a transmission line, or we can say through a Wi-Fi network. But at the receiver side, maybe receiver side will get this one. So it means the sender or the receiver do not have the same amount of data or same data. So this is error, or you can say mistake also, but this is error. So how much error we have? We have how many bits are changed during the communication? There are so many bits are changed during communication. So error is basically the difference between the actual value and the observed value. This is the actual value, or what we have observed at the receiver side, this is. So this is the error. And how many bits has been changed? There are lots of bits has been changed. So there are two types of error. One is a single bit error, another is burst error. Single bit error is those where only one bit has been changed. Like for example, if we have a data like this, and we have received this. So in this communication, only one bit has been changed. So this is called a single bit error. And single bit error can be detected very easily and can be corrected very easily. Detected and corrected very easily. But if we can have more than one bit error, like in this case, more than one bit error, so it is called burst error. The detection of burst error and the correction of burst error is not an easy task. It is very tough task. So what we have to do? We have to do retransmission of data again, just to save our time. How can we detect or correct the data if there are so many errors? Better to retransmit the data again from the sender. So this is the retransmission. If there are burst error, or there are so many errors and we are not able to find the error, we are not able to correct the error, then we can ask the sender to retransmit the data again. So this is the single bit error. A single bit error has been changed. We can detect it, we can correct it. Okay. So burst error means more than 2 bit has been changed during data communication. So this is called burst error. So this is burst error. 1, 2, 3, 4 bit has been changed. So this is the example of burst error. To detect or correct error, we need to send extra bit. Extra bit, what is it? Just how can we ensure, how can we make that this data has got this particular error? To detect this type of error, we have to include some extra bit, which can be treated as a redundant bit, or we can say duplicate bit. Like for example, this can be a redundant bit. This can be a redundant bit. We can apply this. So we can learn what is redundant bit, how can we apply the redundant bit, how can we correct and detect the error in later slides. Okay. So this is a center side, message, generator, and message and redundancy. Redundancy has been applied, has been added, has been applied with the actual data. And this is a reliable transmission where error can be detected. Error can be added to the data. The received information, the checker, and the message. Here, some error has been detected. So either we have to detect the, after detection of the, we have to correct the error, or we have to discard the message and ask the sender to retransmit the message again. So block encoding. We divide our message in blocks and each of k bits called data words. We add r redundant bits to each block and make the length as n is equal to k plus r is the redundant bits. And this resulting n bits are called the code words. Okay. So like for example, this is the actual data. This is the actual data. 2 to the power k data words, each of k bit. 2 to the power n code words, each of n bits, only 2 to the power k of them are valid, other are invalid. Okay. So this is a process of error detection in block encoding. So these are the k bit in data word, the generator, n bit in code word. It transmits through unreliable transmission. The code word is n bit, checker, data word is k bit, and the checker, it has identified that some bit has been changed, so it has to discard it. Discard it means retransmit the data again. But if this particular data is correct, then this is data word. So Hamming distance between two words is the differences, the number of differences between corresponding bit. How? Basically, let's understand with another example. Like for example, 1101. This is a 4-bit data. Okay. This is the sender. Sender send this data. Receiver received this data. How many bits has been changed during the data transmission? No change. There is a change. There is a change. No change. How many bits has been changed? 2 bits has been changed during data transmission. So this is called Hamming. This is called Hamming distance. Hamming distance is the difference between the sending bits and the receiving bits. How many bits has been changed? Now read this example. The Hamming distance D is 2 because only 2 bits has been changed. These 2 bits. Okay. Now see here. Do not check that these 2 bits are changed. Just apply the XOR operation. 1 and 1 0. XOR operation in each bit. 0 and 1 1. 1 and 0 1. 1 and 1 0. So we can apply XOR operation also. Or we can check how many bits are changed. If there are 0 and then 1, it has been changed. So there are 2 bits. The Hamming distance in this and this one, how many bits has been changed? The first bit is same. The second bit has been changed. The third bit is same. The fourth bit has been changed. The fifth bit has been changed. So it means 3 bit has been changed. So how? 1 0 1 0 1. This is the sender side, and 1 1 1 1 0. This is the receiver side. Any operation, like if you are applying the XOR operation, so 1 0 1 0 1 1 0 1 0. 3 bit, 3 ones are there. So it means 3 bit has been changed. Or you can say that the changed bit 1 0, yes, it has been changed. 0 1, it has been changed. 1 1, no change. 0 1, it has been changed. So 3 bit has been changed. So Hamming distance is a very simple formula. How many bits has been changed during the data communication? It will change 0 to 1 or 1 to 0. So just count how many bits are changed. So this is the Hamming distance. Okay. So the minimum Hamming distance is the smallest. The minimum Hamming distance is the smallest Hamming distance between all pairs in a set of words. In a linear block code, the exclusive XOR or of any 2 valid code word create another valid code word. Next, a simple parity check code can detect an odd number of errors. So this is another example. Cyclic code are special linear code blocks with one extra property. In cyclic code, if a code word is cyclic, shifted the resultant the code word, like in this example. So before understanding this, we can understand this type of a simple parity check. What is parity check? Like for example, if I am asking that an ASCII character is how many bit long? A character, a byte, how many bit long? Everyone saying 8. No, it's not 8. It's 7 bit long. Even the ASCII character is 7 bit long. So if the ASCII character is 7 bit long, you can check it. A stands for 65, and you can check it, the conversion of 65 into binary. For example, 1 2 3 4 5 6 7. This is the ASCII character. Okay. This we have to transmit to transmit through a channel to receiver. So after transmission, the bit has been changed, but how can we check it? A redundant bit, a parity bit, redundant bit, or we can say parity bit. What is parity bit? Extra bit we have to apply at the right hand side. How? If there are even number of ones, then the extra bit value is a 0. If the even number of ones are odd, here number of ones are odd, so we have to place 1. Okay. Now we have to transmit it through an unravel channel. After that, this has been received. Now again, check the number of ones. 1, 2, 3, 4, 5, 6. Number of ones are 6. It means even. So what is going here? 1 is left. Yes, this one. Yes. Now number of ones is 7. But in this case, we have transferred 6 ones, but what we are getting? 7 ones. So we can detect that one bit has been changed, a single bit has been changed. So this is called single bit error detection, and we can correct it by comparing the data. Okay. If 2 bits has been changed, like for example, this one, now 6, 2 bit has been changed, and we can get the number of ones is 6. It means even. So the receiver understands that there is no error. There is no error. So if the number of bits are changed more than 1, so we can not detect burst error. We can detect only single bit error. If only 1 bit has been changed during data transmission, we can detect and correct it. But if more than 1 bit has been changed during data transmission, it is very tough to detect and correct it. There are many other ways to detect and correct it, so we can check it later. So this is a CRC method, cyclic redundancy check. In cyclic redundancy check, there is a division operation. Like for example, this is the data word. Data word is the actual data which we want to send to the receiver. Okay. This is a divisor. This is a divisor. The divisor is already given to the user based on certain conditions. The divisor can be common to a few users, or it can be generated by using some algorithms. We will discuss it later. But first we will discuss what is in CRC. So in CRC, this is data 1001. So the data length is 4 bit. So we have to apply 3 zeros along with this. These 3 zeros. If the data length, this data length is 6 bit, how many zeros we are applying? 5, just n minus 1. Okay. So now by this divisor, we are dividing, simply dividing. So 1011, now there are XOR operation. We are doing only XOR operation, nothing else. So by using XOR operation, 110, 01, 1, 0, 0, 0, 0, nothing. So this 0 is keeping here, it is not divided. So again, one more 0 has been copied from above, then 1011, again this we are getting, and then this. So this is a remainder. So this is a remainder. So what we have to do, along with this data, 1001, we have to put redundant bit here. 110, this 110 in this way, data word and the remainder. So this is the code word. So understand, this is the data word which we have to send from this side to this side, and after applying the CRC method, the remainder has been added as a redundant bit along with the data. It is called code word. Okay. And at the receiver side, what is happening? At the receiver side, this code word 1001, again divided by this 1011. This divided 1011. What happens again? Now, if we are dividing the code word by using the same divisor, the remainder should be 0. If the remainder is 0, then there is no error. If the remainder is not 0, so it means the code word has some error. We have to correct it. If there is only single bit error, we can correct it very easily. If there are burst error, we have to ask sender to retransmit the data again. So this is how we are dividing in CRC method. Okay. So this is the case. 110 we have to put and find 000. It means there is no error. But in this case, if the data has been changed like this, data has been changed. The data sent by this is 1, but the changed. Now this is the error. If this is error, it means there is a burst error. So we have to discard it and the retransmission of this data again. Okay. So this CRC method uses some polynomial concept also. Okay. Like for example, if I am saying 1100, okay. So this is x to the power, sorry, this is 0, this is x to the power 0, x to the power 1, x to the power 2, like in this way. So this is x to the power 3, x plus 1. So we have to learn how this binary number into converted into some algebraic expressions. Okay, which of these following GX value generate a single bit error is caught for each cases? What is the error cannot be caught? X plus 1, x cube and 1. Now understand, x to the power I can be divisible by no x to the power I can be divisible by x plus 1. So we are talking about this case. So any single bit error can be caught by using this. Now we are talking this. If I is equals to or greater than 3, then x to the power I is divisible by gx and all single bit error in the position 1, 2, 3 are caught. All values of I make x to the power I divisible by gx, no single bit error can be caught. So this gx, this particular gx is invalid. It is useless. We cannot use this. However, these are also not good to use as a divisor. We cannot use these because these divisors can be used for special conditions only. So this is another example. X plus 1. This is a very poor choice for a generator. Any two error next to each cannot be detected. This generator cannot detect two errors that are 4 position apart. This is a good choice. Yes, this is a good choice, but this is a very long, very hard, very tough to apply it. This is also, but this polynomial cannot divide x to the power t plus 1 if t is less than 32,768 because the number is very high. So we have to make certain rules to decide the divisor. A generator that, what are the rule? The first rule is the generator that contain a factor of x plus 1 can detect odd numbers error. So this is the rule 1, that the divisor should be a factor of x plus 1. Okay. So these are the, this one or this one. So ABC. The generator can detect all burst error. Can all burst error. Because this has the factor of x plus 1. But everyone has some limitations. Okay. So based on these limitations, we have to decide what type of generator or divisor we have to decide it. So these are the some rules. It should have at least 2 terms, minimum 2 terms. The coefficient of the term x0 should be 1. X to the power 0 can be treated as a 1. It should not divide x to the power t plus 1 for t between 2 to the n minus 1. And it should have a factor of x plus 1. So these 4 are the thumb rule to decide the divisor, or we can say polynomial generator. Okay. Now checksum. Checksum is another method to detect or correct the error. This is the last method we will discuss here. The checksum basically used with various protocols, like if we are talking about some internet protocol, IP, TCP protocol, ARP, RARP, maximum times of frame formats we are using checksum. So checksum is what? Let's understand it very easily first. Like for example, this is a checksum side, this is a sender side. Sender sends some values. Sender sends some values, and the sender applies some redundant bit along with this checksum, along with the data word, to make it code word. So what we have to do, make it in bits form. Like for example, we can understand in this way, like 7, 11, 12, 0, 6. These are the data. 7 plus 11 plus 12 plus 0 plus 6 plus 0. We have to add this. 36. Okay. Wrapped sum 6 and checksum 9. So, to understand this, better to take this example. Like for example, we have to deliver this FOROUZAN. Okay. FO. The hexadecimal of FO is 466F. RO. This one. So this is the hexadecimal codes. This is hexadecimal codes, and we have to add all hexadecimal codes. So these are the addition of hexadecimal codes. Okay. Now what we have to do? This is the sum, and this is the ones complement of this hexadecimal code. Like for example, we have to do some numerical example, short numerical example we have to do in this way. Like for example, 1, like for example, 1 1 1 0 1 0 0 0 4 5 6. This is the case. Okay, you have to divide into blocks of 4 bits or 8 bit. How many bit long is the checksum we are needed? Just for example, we are having 8 bits. So 4, 4, and to make it 4, this one. So what we have to do? 0 0 1 1. Next 1 0 1 1. Sorry, 1 0. Next is 0 1 0 1. Add 1 or 1, 0, 1 carry. 1 or 1, 0, 1 carry. 0 plus 1, 1. 1 or 1, 0, 1 carry. 1 or 1, 0, 1 carry. This one has been added to this side. So 1 1 0 0. Okay. This is a sum of this data divided into block of 4 bits. Now what we have to do? Take ones complement. Ones complement is 0 0 1 1. This ones complement. So this is the code. This is the data word, and this is the code word. 0 0 1 1 1 0 1 0 0 1 0 1, and these 4 bits 1 1 1 1 0 0. This is the code word. So what we have did here, after adding these, we have to take ones complement and we have to put this 4 bit at the right hand side. So this is the code word. At the receiver side, what it will do? It will again add this one, this one, this one, and this one. Again add. What it will get? It will get 1 1 1 1. If it will get all ones, it means the data has no error. If it will get anything, any 0, or it will not get 1 1 1 all ones, then it means data has some error. Like now, in this case, no, in this case, see, so this is the sum and this is a checksum. Checksum, it means we have to find the 16th complement because it is hexadecimal code. So you have to subtract 15, you have to subtract this from 15. 15 minus 7, 8. 15 minus C is 13. 15 minus F, 0, because F is treated as 15 now. 15 minus 8 is 7. So this again has been added in this case. In this case, so what we get? F. E. So the carry has been added to this. So FFF, all F are there. So if we get all F, it means everything is like this. So we can say that the checksum is 100% correct. So this is how we can get the checksum. So these all about the error correction and detection. One more technique is the remaining, Hamming code. So we will discuss the Hamming code later. So in a summarization, what we can say that error is the difference between the actual and observed value. There are two types of error. One is single bit error, another is burst error. Single bit error can be detected and corrected very easily, while in the case of burst error, we can ask user to resend the data again because it is not easy to detect or correct the data. There are various techniques to detect or correct the data. The one technique is to apply the parity bit. Parity bit, basically we are applying even parity. So if the number of ones are odd, we have to apply 1 at the right hand side, make it even number of ones. At the receiver side, if the number of ones are even, then there is no error. If the number of ones are odd, then it may have single bit error. Okay. The next technique is Hamming distance. How many bits has been changed during the data transmission? If one bit has been changed, then it can be detected and corrected very easily. If more than one bit has been changed, then it can be detected, but it is not easy to correct it. The another method is CRC, cyclic redundancy check, which is very important. In the cyclic redundancy check, we have to divide by using some genitive polynomial, genitive GX, the divisor. The choice of divisor, how can we can decide the divisor? There are 4 thumb rules, and these thumb rules are these thumb rules. 2 terms, the coefficient of the terms x to the power 0 should be 1. It should not divide x to the t plus 1, and it should have a factor of x plus 1. Another method is checksum. In checksum, we have to divide in 4-bit or 8-bit. If we have to do this by using 8-bit, so 4, 4, 8, this 4th we have to put some zeros at left hand side, and we have to add 8-bit data. So this is the example of checksum. Let's take another example. No, this is not for use. So this is the only example. So we can understand the checksum very easily. Checksum basically, if you study the IEEE frame format, the IP header format, the TCP header format, the UDP header format, the ARP header format, everywhere the checksum is in use, because checksum play a very important role to find the error and to correct the errors. Okay. So this is all for this lecture, and thank you very much.